Counter instructions. Counting events, not units of time. Whereas timer data types accumulate units of time in 1,000th of a second increments, which in itself is a fixed event, counter data types accumulate the occurrences of events unrelated to time. Namely, they accumulate the occurrence of each false to true transition of the run condition out from the collective state of the conditions preceding the counter instruction in the run. Also, regarding timer data types, other than the reset instruction, an instance of a timer instruction such as TON, TOF, or an RTO is executed against a unique instance of a timer data type for each instance of a timer instruction. Counter instructions, such as count up and count down, can both execute against a single instance for both instructions. In other words, with TONs, RTOs, TOFs, you normally would not execute two of those instruction types against one single instance of a timer data type. In other words, you wouldn't have a run that goes true that executes a TON on, say, the instance of timer data type my time in our previous project, and then turn around and have a run go true that exercises an RTO against that same instance of a timer data type. That would be highly unusual, unpredictable, and frowned upon. However, with counter instructions such as count up and count down, it's very common to execute both of those instructions against a single instance of the counter data type. Your counter data type has an accumulate and a preset amongst other things like control bits, but basically a count up instruction tells the counter data type to increment, a count down instruction tells it to decrement, hence count up and count down. There is only one type of timer data type and only one type of counter data type, and it is the instruction that affects unique results on this data type. Emphasis on this: there is not a count up data type and a count down data type. There is just a counter data type. And the instruction either increments the value in the accumulate member of the counter data type, or it decrements the value in the accumulate member of the instance of that data type. Think of an instance of a counter data type as a pre-designed tray with specifically divided spaces of different dimension. Some with 32 spaces for double integers, some with 16 spaces for integers, some with 8 spaces, single integer, and some with unique individual spaces, Boolean for one item. You can have more than one person putting in and taking items from, that is, putting in and taking out zeros and ones from one tray. You can have more than one instruction acting on a single data object. If you have two people working on a tray with components or parts and little bins or compartments, one person can be putting parts in and another person taking parts out. Think of the count up and the count down instruction against a single counter data type in that way. We had you create a new project named beginner L your processor number underscore count up, added underscore 00. At this point in your learning process, you should be able to explore the tabbed instruction categories and find the instructions that are used in the lab projects. I stretched the language element bar as wide as I could and still could not expose all of the tabbed elements. Spend some time in exploring each of these tabs. As far as what you saw in the manual, that was too, I can read it with a good pair of glasses and a strong light, but just barely. So you actually need to go into the software as we have it here, and I can take and drag this out to the full width of the screen. Matter of fact, just for grins, I'll pull this down to here. And I'll drag this all the way over to here and all the way over as far as I can this way. You see, I have that exposed as wide as I could make it, and I still cannot expose all the tabs. So if we start from one end, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. Oh, maybe that is the last one. So you see there's a bunch of tabs there. And as you click on each tab, and of course it won't cooperate because I need to go here to get it to cooperate. It means I have to be in the programming area. So as I go here, add on, there's favorites, and you can modify what's in this list. Add on, we have none, not really. Add on data types, add on instructions. We haven't created any. That's an advanced subject. You can create your own instructions. Alarms, bit, timer counter, input, output, message, get system variable, set system variable, immediate output update tag, comparison, compare, limit, mask, equal, equal, not equal, less than, greater than, less than, equal to, greater than, equal to. Compute is the compute right there, and then there's add, subtract, multiply, divide, and modulo, square root, negate, and absolute value. Those are mathematical functions. Move, it's really not a move, it's a word copy. So that's move with mask, and or exclusive or. Swap byte, in other words, you can take the 2 bytes of the integer and swap them. Not, it's a logical function. Clear, any register, and bit distribute. Bit fill distribute, that's a really cool instruction. We'll get to that in one of the later volumes, not in this volume. File, arithmetic and logic, file search and compare, file copy. Whereas move is a word copy, COP is a file copy. So you copy a length from one source to a destination. File fill, you can fill a whole file with one particular value. So you see the source is the value, the destination and length is what you want to fill it with. Average file, sort, standard deviation, size and elements, and file synchronous copy. So we can go on and on here. Bit shift left, bit shift right, FIFO load, FIFO unload, LIFO load, LIFO unload, sequencer in, sequencer out, sequencer load, jump, label, jump to subroutine, jump to external routine, return, subroutine label, temporary end, master control reset, user interrupt disable, user interrupt enable, reset sequential function chart, pause sequential chart, end of transition, trigger event task, always false. Now that's an instruction that some people move to their favorites, because if you want to create a rung that is bits and you're using that almost like an HMI, in other words, you're watching the state of those bits, but you don't want to turn anything on and off with that rung, then you put an AFI. And of course no operation. So actually always false you put in front of the rung, so the rung's always false, and at the end you can put a no op. For break, PID, well, that is one heavy duty instruction. So trigonomic, trig functions, natural log, log base 10, x to power of y. There's just, I'm not going to go through all these. Then these are all motion instructions. every one of these tabs. Then ASCII, you've got all of these tags for ASCII operations. That's the end of it right there. So I guess I didn't try hard enough to stretch them all out before, but you can see there's a bunch there. Well, we're not really interested in 90% of these, not even 95%. We're right at the very basic level. You need to conquer the basic level in writing basic code, sequential logic, machine control, before you muddy up your brain with all these other instructions. So there's a long way to go to cover everything. We're not going to cover even a small portion of this in this manual. As a matter of fact, you already know that once we cover the counter instructions, then we pretty much take everything we've learned so far and we keep building it into this 3-conveyor project. We started out and had you add these 4 rungs to a fresh project. Now you could have deleted all the code from the previous, deleted all the program tags, and then saved it as beginner L whatever your processor is, CTU _00, or even just CTU. Remember, I add the 00 so I can go 01, 02 for different revs of the project. All tags are scoped as program tags. After you added the logic and defined the tags, I had you open the program tag database. Of course, this is what you find. You have count 1 complete, and that is aliased to local 10 data 0. And then you have the less push button, more push button, and start over push button for reset. And of course you have the counter. I had you open up the counter, and we could go back and do it in the monitor if you like that better. So you can see that there is only one counter data type used, one instance of that class of objects. That's the only counter data type that you can find. If you look down through the data types there, you only see one, counter 1. This is a data object, counter, made up of the members .acc, the accumulate, which is a double integer, .cd, control, which is a Boolean, that's count down. CD is count down, CU is count up. You have a done bit, these are all Boolean. You have an overflow, which is Boolean. Then you have a preset, which is a dent. Now you can always expand these out to 32 bits. That's really a waste of time. We don't care what the individual bits look. And then of course you have the undercount. If we go to instruction help, drag this down, go down to timer counter instructions, time counter. And then we work our way over here to count up, overflow. There you go. The underflow bit indicates the counter exceeded the lower limit. If you look through the description here for count up and count down, you're going to find that they're very similar, except if you count up you have overflow, and if you count down you have underflow. But the main thing is that you have a lower limit of 2,147,483,647 and a high limit of 2,147,483,647. Your range to count, this is the lowest limit, that's the lower the limit, and this is the higher. Now what happens, the counter then rolls over. So if you keep counting down to minus 2,147,483,647, if you count down one more time, it rolls over to the high end. So it rolls completely over, folds completely back over. And it'll turn on the underflow bit to warn you that that's what happened. So these instructions are really quite straightforward. I usually never put them in a position where they can overflow or underflow. As a matter of fact, I usually add a little logic so there's no way it can overflow and underflow. Even if I have to put in logic that resets the counter or stops the machine if it gets too close to overflow or underflow. So download your new project and go online in the run mode, all inputs off. Remember, you had some inputs on from the last project. Communications, who active, processor is selected, download, downloading. Isn't this much quicker than RS-232? Amazing. Okay, now we're downloaded. So we'll close this and come back up here. And the done bit is set. And of course it turned on that output, the red light on your digital field device simulator. The reason it's on is because your preset is set at 0, the accumulate 0, therefore it's done. I did not have you put any value in there. Within the graphic icon, countdown, select the preset value and type in, well, wait a minute, download your project, go online in run mode, all inputs off. Is the done bit on? Yes. Within the graphic icon, count up, select the preset value and type in 5. Is the done bit on? No. Did the instruction accept the value of 5? Also, I would ask you, do you see the same preset in both instructions? Well, of course you do, because counter 1, the preset's 5 and the accumulate is 0. So either one of these are going to read the exact same values because it's the same data structure. It's the same instance of a counter data type. Did the instruction, well, I had you change this back to 0. So I did the 5 here, let's do the 0 down here. And see, no matter where I do it, it takes effect. Did the instruction accept the value of 0? Yes. Did the value entered into the count up affect the value in the count down, or the value entered into the count down affect the value in the count up? Yes. Why? Because you're viewing the status of a single data object, a counter data type. There is only one preset for an instance, counter 1, of a counter data type. If there are outputs on, they were left that way from an earlier project. Toggle them off in the monitor view of the controller tags database. Well, I don't have any bits on except for this output right here that's being controlled by the done bit. Change the value of the preset to 5 while observing the members of the instance of a counter data type named counter1. Switch more PE to the on state and leave it in the on state. So first we put in 5 and then we turn on the more switch, which is input 0. And notice that the accumulate in both displays here went to 1, because remember there's only one counter 1. That's one instance. What is the accumulate value in the count up icon? 1. What is the accumulate value in the count down icon? 1. Now remember, these are all somewhat rhetorical questions. The reason that I put them in the book and I put blanks in here for you to write is to make sure that you look, make note, and write it down. If you were just reading, you might run right over this, but if you have to stop and think and write it down, you're more apt to remember it. While observing the members of the instance of a counter data type named counter1, switch less PE to the on state. What is the accumulate value in the count up icon? 0. What is the accumulate value in the count down icon? 0. While observing the members of the instance of a counter data type named counter1, switch more PE to the off state. What did the accumulate value in the count up? What is the accumulate value in the count up icon? 0. What is the value in the accumulate value in the countdown icon? 0. These instructions execute on a false to true transition. We just went from true to false. Obviously, nothing's going to happen. While observing the members of the instance of a counter data type named counter1, switch less PE to the off state. What is the accumulate value in the CTU icon? 0. What is the accumulate value in the countdown icon? 0. Now the reason we keep repeating this is to firmly cement this behavior in your mind, and the reason that I incessantly keep repeating the instance of a counter data type, the instance of a timer data type, the instance of this type data type and that type data type, is to firmly implant into your mind that these are instances of a class of objects over here in data types. We go to predefined, and we can find counter right there. Double click. You cannot edit this. This is a class of objects, and these are the members. Preset, accumulate, count up, count down, done, overflow, and underflow. This is the class of objects, and this is an instance of this class of objects. This whole philosophy permeates Logix 5000. All reputable controllers are going this direction with information object modeling. It is absolutely phenomenal, the benefits of using this type of data structure. It's more of a three-dimensional data structure than a flat data table. While observing the members of the instance of a counter data type named counter1, switch more PE to the on state and back to the off state. So go on and off. What is the accumulate value in the count up icon? 1. What is the accumulate value in the countdown icon? 1. While observing the members of the instance of a counter data type named counter1, switch less PE to the on state and back to off. On and back to off. What's the value in both count up and count down? 0. Review the above results before you answer this question. Which action, and that one alone, effected a change in the accumulate value? A false to true transition of that rung. We did true to false, and that did not change the accumulate. But anytime that we did a false to true, rung out condition of those conditions there in rung 0 and 1, it affected the accumulate value. The count up and count down instructions are actually each comprised of simple instructions, one of which is a one-shot instruction that only allows one execution of the increment or one execution of the decrement of the accumulated register for each leading edge of a false to true transition of the rung condition out, immediately preceding the count up or count down instruction. Somewhere in the distant future, you will create your own unique instructions with an RSLogix 5000 feature that allows add-on instructions. For now, let's concentrate on the most basic instructions available to you from just a few tabs on the language element toolbar. I did point out in the manual that we were going to mix it up as far as the labels on these inputs that initiate or trigger the count up and the count down instructions. So to make this more closely match, I'm not going to create a new tag, I'm going to edit. As a matter of fact, let me back up. I did something I did not need to do. So I'm going to delete or cancel pending rung edits. I don't need to put the rung in the edit mode to edit that tag. I'm going to make that an E for photo eye instead of push button. But I'll leave this one as a push button. Or, because it says PE in the manual, maybe I'll just make it an E. Either way, my point is these are field devices, whether it's a push button, a photo eye, a solid state switch on some device like a barcode reader, and this is an interface to the barcode reader to count up a qualified read from the barcode reader, and you're counting qualified reads, good reads versus bad reads. It really doesn't matter what these devices are. They're just digital inputs. Toggle more PE on off until the accum is equal to 5. Right now it's 0. And 2, 3, 4, 5. What is the accum value in the CTU icon? 5. What's the accum value in the CTD icon? 5. What is the state of the done bit? The done bit is on. And of course our red light is on our digital field device simulator. Toggle more PE once more. What is the accum value in both of the icons? 6. What is the state of the done bit? 1. on. Toggle more PE on off several more times. 7, 8, 9, 10, 11, 12, on and on. What is the accum value? Well, I said several more times, so you could have anything from 7 to whatever, but you have more than 5. What is the state of the done bit? The done bit is on. How does this differ from the behavior of the timer data type when the accum value equaled the preset value? Ignore the one instance where we manipulated the timer data type from the keyboard and witnessed that anomaly where it started timing again and it went from 10,000 to 10,001. Ignore that. Okay, so answer the question, how does this differ? With the timer data type, when it's done, it's done. It's not going to go any further. It's not going to count any more units of time under any kind of normal circumstances. However, with the counter, it just keeps on counting up until you hit, what was it, 2 billion and something. The done bit is on anytime the preset is equal to the accumulate or more or greater. The preset is equal to or greater than the accumulate, then the done bit will be on. Toggle less on off until the accum is equal to 5. 6, 5. What is the accum value in both icons? 5. What is the state of the done bit? It's on. Toggle less until the accum is equal to 4, or rather once more. What is the accum value? 4. What is the state of the done bit? It's off. Toggle less on off until the accum is equal to 0. What's the accum value? 0. What's the done bit? It's still off. Toggle less one more time. What's the accum value? -1. What's the state of the done bit? It's off. Now, we went through all of this detailed iteration to give you the opportunity to see the behavior of the counter data type with the accumulated equal to the preset, greater than the preset, counted back down to the preset, counted below the preset, counted down to 0, and counted to a value under 0. How high and how low of a value can you realize with a counter data type? I had you select help from the main menu. Well, we'll do that again. Instruction help, timer counter instructions, count up. There you go right there. Low limit of -2 billion, high limit over 2 billion. Honestly, who can count that high? And what could you possibly want to count that high? That's the nice thing of the Logix engine over the 500 engine, the MicroLogix engine, and that is with Slick 500 and MicroLogix, they had a limit just over 32,500 positive and negative. It was signed integer, which means the bit 15, or the highest, the most significant bit, was the sign. If it was 1, it was negative. If it was 0, it was positive. So you didn't even have 16 bits to work with, only 15. And you can create your own add-on instruction that will count higher or lower than the limit shown here. Now, we're not going to explain here why. Toggle start over, which is input 2. Notice that resets everything. Toggle more on off several times. What is the accum value? 2. Why? Because that's how many times you went from false to true on rung 0. Toggle start over and to the off state and leave it off. Now, the reason that I stated it that way is if you have a toggle switch, normally when we say toggle, you know, in terms of this functionality right here, toggle bit, that means to literally toggle it from one state to the other, whatever state it's in. Quite often when we're talking about a toggle switch, you could argue whether toggle means to change state or go from one position to the other and back again. Not quite sure the best way to word that. Nonetheless, take the reset, start over to the off state and leave it off. Edit your logic as shown in the manual and finalize all edits. So we took rung 0, put it in the edit mode, and then we simply can go right click, copy, right click, paste, and we have the edits done. So we have two count up instructions, both manipulating the same counter data type. Now we did this, and we're going to do several different things like this so you can clearly see the totality of the behavior of the count up instruction and how it behaves in logic. Toggle more PE on off 2 times. 1, 2. What is the Q value? 2. Did both count up instructions execute individually? I'm going to say no, because when I make that rung go true, the true state passes through that first count up instruction to the second one. But remember that these two count up instructions are executing against the same counter data type. So in this case, the count up instruction, the counter 0, 1, the counter data type, at the end of the rung, so to speak, it only sees one false to true transition, even though you have two count up instructions here. Then we had you throw in another permissive or another condition, and we called that one more PE. So see, I'm double clicking on it. I'm not right clicking and editing. One more PE, and of course that is not a defined tag, so we'll go define it. And we're online, so we want to alias it now to input 3. Local 1i data 3. Finalize all edits, and it's done. Boy, that's quick. Ethernet is wonderful. Switch one more PE to the on state and leave it there. So we're going to flip one more PE on. What is the accumulate value? Let's do that again. It doesn't change. Now why would this going true not change anything? Well, the rung's not true, is it? So neither one of these instructions see a false to true transition. However, in the manual, I actually told you to toggle the more PE on and off 2 times. So we have input 3 on, so let's do more PE 1, 2 times. And the question was, did these execute independently? No, they didn't. At the end of the rung, this counter data type, counter 1, still only saw one false to true transition. Remember that both these instructions are addressing that counter data type. So if both of them basically simultaneously send a CU bit, count up, well, the data type's only going to count up once. It doesn't matter how many count up instructions you have in this rung like this. Switch one more PE to the off state and leave it there. And then do more PE. So now this bit is off. So the rung out condition here is going to be false. Now you see what happened? Here, this is really interesting. You don't have to remember this. You don't even really have to understand this. But think about what we did. This is false, and this is true when we push the button. So if I flip that switch on and leave it on, which I can do with this simulator, you see what it's doing? It's basically scan counting. So this true out initiates a count up bit, but then this is false. The false execution resets this. Next scan around, this is true, counts. False, resets it. So this rung is resetting this counter. It's resetting the false to true state. not the count value. So every single scan, this is incrementing. The first time 0 goes true. We'll do these start over thing just so we have a clear shot here. So if I turn this on, that goes true, that increments. This is false. It clears the false true memory, if you like, the one shot. And then the next scan around, it can count again. So you basically, by doing this, have turned it into a scan counter. You don't want to do this. So I'm going to turn that off. And of course, if I go back here, turn that on, and then I turn on this one, see, now it stops doing that. And then as I go on and off with more PE, now they're back executing normally. So that's something to think about. Now, I don't know why anybody would even try doing this, actually writing code. But we're trying to be very exhaustive in how we treat these very, very basic instructions. I think that when you first start programming, that you're going to be so focused on coming up with code that matches the process that you're not going to try to do anything crazy like this. If these were two different counter data types, counter 1 and counter 2, that would be a different story. In the manual, I had you leave more PE on, one more PE off, to let this accumulate up to the maximum. However, we don't want to wait that long, so select it and then type in 214747 1234. Okay, that gets us close as you see what happened. We counted up, it got to the maximum and rolled over to the bottom. Now it's counting up from the bottom. It'll keep right on counting up. We'll put in minus 2000. Yep, back into the positive. See, it counted, it just keeps counting round. Meaning, if you're counting up, it goes all the way to the maximum and then rolls over to the bottom and starts up again. From the lowest value back up to the highest value. The count down instruction is going to do just the opposite. It's going to count all the way down to the lowest minus number and then swing around to the most positive number and work its way down again. Now you know two things that you might not have realized before about these instructions. Do not write logic that uses the instructions as we did here. You ended up with a scan counter. Don't have two count up instructions in the same rung working against the same counter data type. You're liable to end up with irregular behavior, unless you want a scan counter. When the instruction increments the counter data type one past the maximum, it makes the bit 31 on the dent a 1, which implies a negative value of the previous count of 2,147,483,647. To demonstrate that, I'm going to put that value in there. 2,147,483,647. Okay? Now see, it's done because it's more than 5, but I'm going to hit the more PE one time. See what it did? It went to minus. So when you overflow, it just keeps right on counting. Those are two things. Now I had you edit your logic. I'm going to pause, do that, and then come back, not make you watch me do it. Well, why not? I'll let you watch me cheat. So I'm going to take a new rung. I'm going to select this, and then Control, select this. I'm going to bring it down to here. I still have to put this rung in the edit mode to delete those two instructions. Finalize all edits. And this should match what was in the manual, other than let's hit start over to get rid of those big ugly numbers. So we had more PE, true of fun, count up, counter 1. One more PE, count up, counter 1, and then we had less count down. switch more PE on or one more PB on and leave it in the on state. Doesn't matter which one. So we'll put one more on. Well, now you have some interesting behavior, don't you? And I think you can explain this one. Again, we have a scan counter. What's happening here? This rung is false. So the false execution of a count up is to reset its one shot that allows it to increment only once on a false to true transition. But the very next rung is true, so it increments. And then the next scan around sets it to false, sets it to true, sets it to false, sets it to true. Well, the question was, what happened? I just explained it. What is the moral of the story here? Don't use two count up instructions against the same counter. Now, there is one instance where you can get away with that. The only instance that I can think of, or the only scenario where you could get away with that, is if both CTUs are not being executed. Now think about that for a minute. A CTU and a CTD instruction, they have true execution and false execution. So if the rung is being scanned, they are being executed. It would have to be a situation where you had logic that was in subroutines, so not all the subroutines were being executed every program scan. For instance, and we haven't gotten to JSRs yet, jump to subroutines, but you could have conditions on a jump to subroutine where it would run one subroutine or the other, but not both. So you could have 7 conveyors running parts into a bin, and you want to count the parts into the bin. And you have 7 different subroutines, one for each of the conveyors. And then you have logic that selects only one subroutine to execute. If this additional rung right here, if this rung was in another subroutine and it was not being executed, then the counter data type would never see the false state out. It would only see this rung. That is the only instance I can think of where you might get away with having these 2 rungs in a program where they were in separate subroutines, and both subroutines would never be run simultaneously. I would avoid that kind of spaghetti logic though. Now if I turn it off, you see it stops. If I turn the top one on, you get the same behavior, right? If I turn the second one on and then just do one of them, anytime that it's on or off, see? Whoops, hit the wrong one. They're both on, it stops. If one on and the other's off, so there is no way to bail yourself out with this kind of code. Let's change the logic again. Now with less PB, we're going to take and add another counter. So put that in the edit mode, right click, copy instruction, right click, paste. So now we have 2 countdowns. However, we want to switch over to not executing count up and count downs against a single instance of the counter data type. We don't want to edit counter properties. We want to double click, which it won't let us change that in the run mode. So we're going to have to put the rung in the edit mode, double click on the tag name, change it to counter 2, and of course that's a undefined, not unidentified, undefined tag, counter 2. It knows that it's supposed to be a counter data type because it's in a counter. Create, and then down here, when we backspace and do 2, that is a tag because we just defined it. So now we can finalize all edits. We still have a little bit more to do because now we need another rung like this. Control C, Control V. We want to make this counter 2 done, and we want to make this counter 2 complete. And of course that's not a tag, so we're going to have to go define it, but we want to alias it to output 1. Local 1 O data 1. Now that we have 2 counter data types, the reset will also have to be modified. So we could do Control C, Control V to throw in another one. It doesn't matter what order they're in. I think it reads easier if you put them in alphanumeric order, or at least numeric order. So we have count 1, counter 2, counter 1, counter 2, counter 1, counter 2, counter 1, counter 2. It just reads more organized to do it that way, but it really doesn't make any difference what order these rungs are in or the instructions inside of the rungs. While observing the values of each counter data type, toggle more PE on off until the accum equals 6 or more. Okay. Did the count up instructions interfere with each other or with the other instance of a counter data type? No, they didn't. While observing the values of each counter data type, toggle less PE on and off a couple times. Did the count down instructions interfere with each other or with the other instances of the counter data type? No, they didn't. While observing the values of each counter data type, toggle start over. Did you observe any conflict at all with this logic and what you were expecting for results? The answer should have been no. Everything behaved as expected. Remember, when this run goes true right here, this is not the same instance of the counter data type that this is. So when this goes from false to true, and we can do that, notice that they both count down. However, to make sure that you see that they are working independently, let's do, okay, you see this one's now 3 and that one's 1. So if I do less, photo I, 2 minus 2, 1 minus 3, you see, they're independent. Okay, then I had you edit your logic for something a little bit different. In other words, we're going to put the count ups in one rung and put the count downs in separate rungs. And I'll just go ahead and do that in front of you. So I need to put this in the edit mode and then take this count up here and drag it up there. And I'm not really moving it because this rung is not in the edit mode. If you click here and drag, you're dragging a copy. You're not actually dragging the instruction. However, if I were to grab something in this rung, which is being edited, and move it, which I can't because there's no place to drop it, you are moving it, not just taking a copy. So be careful what you're doing. In the less, and it looks like we're not going to use one more anymore, so we can delete this rung. And then for countdown, we need another rung. And we're going to drag this down to here, except that we're not really moving it. See, it stayed there. To change that, I have to put that rung in the edit mode, hit delete. Now that's just counter 1. And then down here, I have to I'll copy this one and bring it down. See, let's undo that. I'll go up here to undo. Now if I grab this one and bring it down, see, it thinks I'm editing, so it thinks I wanted to move it. I didn't. But this is the rung that's being run. It's not, you can't edit it. So if I mouse over and drag down, I'm taking a copy of it. Now this one's going to be one more less, which is not a tag, so we'll just go ahead and type in the text. And you see that it's undefined. So we'll go define it, alias, drill down to local 1i data 4. Okay, now I'm going to finalize all edits to see if I missed anything. I have more PE with counter 1 and counter 2 count up, less PE with counter 1, one more less PE for counter 2, counter 1, counter 2 complete, and then resets. While observing the values of each counter data type, toggle more PE on off until the cum equals 6 or more. Now everything's reset to 0. If it isn't, you should hit start over, that last rung down there. Okay, so we wanted you to toggle more PE until it equals 6 or more. Notice we didn't want to be just done, but one more than done, or two more, but more than done. Now toggle one more less PE on off a couple times, which is input 4. Look at the values, look at the cum values. While observing the values of each counter data type, toggle less PE on off a couple times. Less PE is input 1. While observing the values of each counter data type, toggle one more less on off a couple times. One more less is 4. Do the countdown instructions interfere with the other counter data types? Absolutely not. So you can see the 2 count up instructions, because they are addressing 2 unique instances of the counter data type in memory, operate independently. Each of those 2 counter data types sees the false to true transition of that rung. So we've done this both ways now. 2 countdowns in one rung, 2 count ups in one rung. We have experienced a number of you can do this and you do not want to do this scenarios with the instructions that execute against the counter data type. There are many more arrangements that function as expected, and more than that, that do not function as expected. In other words, there are more arrangements that don't function as you would expect than there are ones that do. Always avoid clever, convoluted logic with any of these instructions, not just the counter instructions. Okay, save your project as beginner L, your processor number, CTU, CTD, RES, because it covered all the instructions. So we'll do that. Go up to File, Save As, and this is the last exercise in the counter section, CTD _ RES. So we'll save this. That's the final phase of this particular lab.